northern Italy, south of Milan. Anyway, he, I think, put the good word out here on us, and that's how we got this invite, and we certainly appreciate it, and appreciate everyone taking their time out of off the end of your day to take in our discussion here. So, as mentioned, my name is Mark Schumacher. I'm a civil engineer, and 90% of my CV is all involves over a number of decades, all involves work with precast concrete elements, everything from concrete pipes to structural precast, and also involved in sales of equipment for that industry as well. So I have a long background in precast, and that's how I came to meet the inventor of this technology as an Italian, but he has a dual citizenship in the U.S. His name is Claudio Sabacchi, and he's the brilliant mind behind this. And he's a mechanical engineer who also happened to have a PhD in physics. And his family was in the precast concrete industry for a huge number of years. And he also worked for a while in some other industries, has dozens of patents to his name. And then he, due to some health issues with his father, he got back into the concrete industry. And that's how I happened to run into Claudio some years ago. And that's how I ended up getting involved with this FSC, but it's a really exciting technology. Anyway, we'll start. This is a new concept tie, sleeper, whatever term you want to use for the rail industry. There's some other applications. The impetus for this, what we're talking about today as a tie, actually came out of the pipe industry, but it was all about finding a new way to reinforce concrete without using steel, get rid of some of the issues that make steel not the best match for reinforcement, especially in precast elements that are exposed to the environment. And then also, if we take the steel and then concrete ties today, most of it's pre-stressed, as you probably know. If we're taking that out, we suddenly can take advantage of the benefits of using dry cast technology to make mass production of a standard item like this much more efficient and faster and less expensive. Okay, the next. So why do we want to move away from steel? Well, there's a number of reasons, but it's been the Achilles heel of structural concrete for a long time. The picture there is obviously an extreme example, but this is what happens when it eventually gets exposed to the elements. And so you get a combination of air and moisture, can cause a lot of corrosion, and then sometimes other environmental factors, like if you're in a place where they salt the roads in the winter, that also exacerbates the degradation of the steel once those salts get carried into and chlorides get carried into the concrete matrix and come in contact with the steel. Next. So a long-term life cycle for steel reinforced concrete depends on one thing is the high pH environment which OPC or ordinary Portland cement concrete provides, at least initially. It forms a passivity layer around the steel, this high pH environment, and it really helps protect it from corrosion. Next. And then the other necessary item here is providing a minimum depth of cover is mandatory. And there's two parts to it. One is you have to have enough grip, is the way I termed it, between the steel and the concrete. You have to have enough meat around the steel to mobilize the tensile strength of the steel. And then because the stress transfer here between steel and rebar and concrete is by shear. And also depths of cover keep air and water away from the steel. a simple typical beam here, just to illustrate where our forces are going. We have a beam supported on each end. If you put a load on it anywhere near the middle, you're going to create a moment at the bottom, and that's going to be also where stress-induced cracks are going to want to occur. And you want to put your steel as close as you can to the surface because that maximizes the tensile capacity of the steel, but it also, the closer you get to the surface, you have the issues we mentioned before come into play. Now we'll take a look at what a railway tie looks like. It's a little different. It's still a beam, but it's got a different loading mechanism and also a bedding and support mechanism. But it's characterized by two really high, intense wheel loads right over the rails, of course. And those produce a positive moment at the bottom surface of the tie where it's in contact with the ground, and produces a negative moment in the middle, which is significant because, as you can see in the picture on the right, there's a bending action there, and it's going to want to crack absolutely right around the center section of the tie. And you can see there that these are some ties that they've tried to do some patching on the cracks just to keep the elements from getting down into the steel reinforcement at the top. But whether it's the network rail specifications or the MXB or the AREMA standards in the US, North America, they all basically are concerned about these three loading places, the moments at the rail seats and the moments in the center of the tie. And I just see here that Claudio Subacchi has joined the call. He's in the wee hours of the morning. He's in Australia working with a licensee we have there. So welcome, Claudio. And so when I get all the tough questions at the end, he can jump in and answer them. Okay, we can go to the next. So the location of maximum tensile forces in structural concrete are highest at the outer surface layer. But as you said before, the more cover you provide, then the greater the steel area required. So you're just building in cost. So there's an equilibrium there, that fine point that you always try to get to. Another element of concrete is it goes through a natural carbonation process. So that high pH you started with in the beginning, when exposed to carbon dioxide, is going to start slowly declining over time, which is going to reduce your specificity layer, and of course reduce the protection from corrosion. And one of the other elements here is that concrete is naturally porous and will eventually develop cracks. We were making a presentation to the chief structural bridge engineer of a very large international contracting company, and he made the comment that he said, we always have a saying, there's two kinds of concrete, one that's cracked and one that's gonna crack. So it's just something you have to work with the material itself, because it's a very ceramic behaving material. Next. One of the other elements at play here wasn't the driving force behind this invention, but it's certainly become clear to us that there's a big benefit in this area. But steel and concrete both have very high carbon footprints, and steel, as you can see in the text box on the left side, has about exactly double the CO2 per kilogram of the material itself. And because concrete is the most used material on Earth except for water, reinforced concrete accounts for about 80% of all concrete. And concrete is such a useful and inexpensive building material. It's not going anywhere. It just needs to be improved, and the structural part of it needs to be improved as well to make it all last a lot longer. So reduction of the CO2 footprint of reinforced concrete is a really high priority to meet global society's requirements to, get rid of the CO2 as much, releases as much as possible. And concrete, because it's such a common material, it's got to play its part as well. So there's three simple ways you can reduce reinforced concrete, the CO2 footprint. One is you can use a different kind of reinforcing material, which is what we're exploring. The second is by use of low carbon binders. And these have been invented for decades. They've been around for a long time. But the issue is they have a neutral pH. So you no longer have that passivity layer helping you protect it. So it has had a very slow uptake in anything to do where steel reinforcement structural concrete is in play. You can do it with mass slabs and that kind of thing, but it's had very tiny penetration of the market in structural concrete. And the final one, you can simply have ways to reduce the cement, so you use less of it per cubic meter. Okay. So what would an ideal reinforcement for concrete look like? This is some of the questions that Claudio dealt with when he dug into this. Well, you'd want high tensile strength. You'd want a lot of corrosion resistance. You'd want good fire resistance. One of the things with steel is that in buildings, especially, it has to be insulated because it loses its strength rapidly once you hit about 400 degrees C. So in a building fire, you don't want suddenly the steel reinforcement to start getting so weak you have progressive collapse. You'd really like to have some high flexural strength. You'd want low creep. You'd want to locate the reinforcement as close as possible to the surface element because this maximizes the tensile capacity of the reinforcement itself. So you can have a very strong high tensile strength, but you have to keep it away from where the tensile stresses are highest. You just have to use more of it. You'd also want to have something that's going to provide cost savings to everybody compared to what you're doing today. The carbon footprint certainly has got to be an improvement if it's going to get any traction in the marketplace. And it would really be ideal to eliminate shear transfer as the mode of the stress transfer because concrete is very, very poor in tension, and steel will put tensile forces that once it runs it up to the shear force runs up to the tensile strength, then you're starting to pop the concrete. Okay, we got a little video here of just winding a tie. And these are ties that we're working with a European mainland company who was interested in this technology, and they provided us some ties. And we did some winding of their ties for some testing. And this program is still ongoing with this company. But this gives you an idea what we're doing here. So we're winding it under tension, and we'll wind on the windings will be on both sides of the tie. So what we're doing there is we're putting the whole concrete element into a post compression, similar to what you're doing with pre-stressing, but you're doing it afterwards. But you're really the post compression goes throughout the whole concrete element. It's much more even than just a straight pre-stressed piece. So the kind of fibers, these FRPs that we're using, like glass and basalt, they have tensile strengths very high, 4 to 6 times that of steel. They have high corrosion resistance. And basalt in particular also has natural UV resistance because basalt is a naturally occurring mineral. In fact, it's the most common mineral on the Earth's crust. It's basically volcanic-based material. And the production of basalt fiber is very simple. You just melt the basalt and down to a point where you can draw it through and make fibers out of it. And that's it. There's no additives. There's no processing. So it's a very simple material to process into an FRP material for reinforcement. It's got high fire resistance. It's not combustible and has twice the service temperature than as steel does. It's got excellent flexural strength. By winding it in tension, you enable the low modulus of elasticity to deliver a level of flexural strength that's really been previously unattainable by any other reinforcement scheme, which you'll see a kind of a good documentation of that here in the coming slide. Once you wind this in tension, your material has near zero creep, long-term creep. And of course, it's located as close to the surface as possible because it is at the surface. So again, we're providing the same effect as pre-stressing, providing a post-compression to the tie in this case, but it's being done in a very highly efficient procedure. And the cost and the CO2 footprint are both better than what's being done today. The FRP used in this method is less expensive overall than, if you take how much the material costs roving for a tie compared to what the steel costs per tie, it's less. And it has a 30% CO2 footprint savings to go with it. And cracks are really no longer a problem because there's no steel to protect, and because you're putting this concrete element into such post compression, if you stress it and you develop a crack, once the stress has been relieved or taken off, it immediately the post compression will close it. It will close the crack just like that, and just close it up. So here's our little video here. This is a pipe, and again, this whole research started with pipes. Okay, this is a 200 millimeter or 8-inch diameter, inside diameter concrete pipe with a 10 millimeter or a little less than half-inch wall that's been wound with the FSC technology and put into this post compression. And you can see it has a very high degree of flexural strength. When we showed this to the people at MXV, which is owned by the American Association of Railroads, the engineers ended up dubbing it flexible concrete. But if you were to take that same piece and do this test without the reinforcing on the outside, it would shatter before you even saw it move. It would shatter into four pieces. So it's the idea of doing this in tension that's really providing this benefit. So now that we're not trying to do pre-stress ahead of time to produce these pieces, suddenly we have the opportunity to utilize dry cast concrete, which is an immediate stripping process and is very highly productive on a small investment compared to the big carousel or long line plants that people use today to produce pre-stressed sleepers. And again, the tie is post compressed after curing by wrapping in tension with this fiber impregnated with the resin. So dry cast concrete's all around us. Everywhere you look or you walk down the street, whatever, you're going to see dry cast concrete. It's the most common method across the globe for production of high volume precast concrete products. So you see concrete pavers. The lower left, you see concrete pipes. There's literally millions of feet of dry cast concrete pipes under rail lines around the world. The center section there, that's a split block building built up in in northern Pennsylvania in the US, exposed to the elements, very durable, and you can provide it with architectural touches like they have here, but it's a very durable material. Pictures on the left are a pre-stressed hollow core, which is actually a dry cast production process, also a dry cast production process, which some might not know. And in this case, in the lower right corner, that's a hollow core parking garage in Northern Europe, exposed to a lot of freeze thaw cycles, and dry cast just has a very excellent performance out in the environment when it comes to freeze thaw. Okay, one of the features here that of dry cast concrete is the basic of it is you use a very low water cement ratio. Okay, yeah, thanks. And so it allows you to use about 20 to 25% less cement to achieve the same strength requirement. So that's again one of the ways you can cut the CO2 footprint down is just simply using less of the binder. The stiffness of the mix allows the form to be immediately stripped. So on the left side there, that's a simple, back one. Another. That's a block machine. It's quite a manual machine. Most block operations you see are highly automated, but you're making hundreds and hundreds of pieces a day off of the same mold that's locked into that machine you see there. On the right side there is a picture up. Back to next slide, Ronaldo.
Okay.
Okay. On the right here, you see a production of what are called hog and cattle slats for the agricultural industry. These are slats that are placed in cattle and barns, and where they walk across. And it's very critical that the adjacent slabs have the same height, because if they don't, the animals will scuff their hooves, and they'll start having issues and diseases in the hoof. They don't want that. They want them to be the same. But with dry cast concrete, you can produce a density right out of the mold that's so stiff that you can stack them one on top of each other and not lose any dimensional tolerance. And that's just an example of how stiff this material, dry cast material is. Okay, next slide.
Sorry. Here it is.
Okay, yeah. So the product will stand under its own weight to go through the curing cycle, and then you can as you can see in the picture here, the product's been stripped. It's standing there, and the form for this 5-foot inside diameter concrete pipe, 8 feet tall, is being returned to the production station to make another element. So from a machinery standpoint, it's a very low investment compared to a wet cast production system. We got a little video here. It's about 4 minutes long, and we're just showing this so you understand it's what type of production line you would see with a dry cast for rail ties. The product being produced here is not rail ties. It's actually, this factory is set up fundamentally around hog and cattle slats, but when they don't have production for that, they make other products. In this case, these little simple concrete bases. So the mold cavity that you have can be cut up or modified to produce whatever it is that you're looking to do. This is a process, part of the process right now where they're filling the mold and it's vibrating, and the vibration that's used in dry cast is very intense. It's just many times more powerful than the vibration used in consolidating wet cast concrete. because it has to be to get that concrete sort of liquefied to flow and move into spaces. And then the final part of this is a troweling process to smooth the outside, the top surface, but it also provides as it passes over with the vibrators on it, it provides a confinement for the concrete. So to make sure that the top part here is as well consolidated as the as the other side that's been had a longer time with the vibrators on. Now it's going to be demolded. So there's a pallet in the frame there of the crane. And it locks onto it. The mold itself is locked to the vibrating table there. So to make sure that all the vibration goes into the concrete and not make the form rattle on top of the table. And then when he sets it down, now there's a few seconds here where there's compressed air is being introduced into the mold on what's now the top surface. That's to break the suction that's created when you had it the other way and vibrated all that concrete in there. And then it'll start lifting slowly, and then once it knows it's released, it'll go quicker. It's a little herky-jerky, but and now the operator will, once the crane moves away there, will come and oil the piece. So the front end of this production station here, there's only one person operating it. If you had steel reinforcement to drop in there, excuse me, you'd have a second person at least at the front end of the production line here. But the length of that video is 4 minutes if you run it in real time. So in that mold and that size table there that you saw, you would be able to put 4 network rail G44 rail sleepers side by side. So it's a very productive way to go about this. The structural behavior of dry cast, because you've got such a low water cement ratio, you have a rapid increase in compressive strength, and it'll allow you to handle the product and do and have enough compressive strength within 24 hours that you can perform the wrapping operation. Again, we talk about we have reduced shrinkage and creep, and of course the dry cast has very excellent performance to the freeze thaw cycles. So this is a picture of a production hall. It's actually in Germany. Again, this plant mostly produces hog and cattle slats, but they have some other products. These are actually slats that are used in by potato farmers. I've never seen it how it is actually used, but it has these half moon shaped holes in it that they use they set potatoes on there and use them for drying out potatoes coming out of the field. Anyway, the front end is the upper right there. That's the production end, and this is a 5 meter long machine. So here they're making 2 8-foot slats in them, as you see on the middle left there. if that was if you were setting that up for rail ties, you'd be able to produce 8 G44 ties in that mold the way it's set up. And the molds can be made modular, as you see in the lower picture. You have the mold is basically a tub, and then you can have pieces that you insert in there to partition it any way you want for whatever production you require. So you can make shorter ties, you can make longer ties, whatever the need is. You have the ability to customize it. So how does this perform in a structural test? Again, we talked at the beginning there about the moment tests, the moment requirements that both Network Rail and AAR have for rail ties, and the primary focus is on the rail seat moments, which are higher, and then there's tests for the center section negative moment. But here's a test we did, and what we did is we made a very basic tie designed around the original wood dimensions, width of 230 and a height of 180, 8 foot long, and wrapped it and tested it. And then you can see on here the rail seat positive moment that's required by our network rail is the red line in the middle. So you get a very high level of flexural performance and the ability to withstand significant displacement before there's any failure. And this is a just unique for a precast concrete object. This is just very unique behavior, and it's all driven by the winding with an FRP intention. Okay. Carbon footprint savings. So there's binder savings by just not using so much of it. You use 25% less. You can also add to that by utilizing low carbon footprint binders. And really, compared to steel, we're using a low quantity of fiber reinforcing, and some of that's due to putting it right at the surface. And then there's also a small amount of resin used, about 10% of the weight of the fiber. But together, the fiber and the resin have a much lower CO2 footprint than the steel reinforcement does. Okay. So the benefits to doing this, of course, we're going to be able to have a much longer life cycle tie because we're not going to be worried about corrosion. And cracks are not a problem. There's nothing to protect inside, and the post compression that the tie is under, once the rail car goes by, if there's any kind of crack, it's going to close right up due to this post compression, and so it'll stand very high cyclic loadings, which is a characteristic of rail ties for sure. It's quite easy to produce, and you can also make low volumes of custom shaped sleepers, but the ease of production and the high productivity of the production system, the dry cast system, will improve and lower the cost of ties. Again, we're not much worried about relaxation losses since we don't have any steel embedded in the concrete, and the FRP is already wound in tension. And doing it that way, there is no creep, so we're not going to have worries about relaxation losses. With no metal inside, the only metal in the tie will be will involve the plates and so on that are the connection system with the rail. But otherwise, they have no inherent conductivity to the tie at all. Again, cost savings. And next. This is one of the benefit, the FRP system will provide a significant dampening effect for vibrations. And also, again, the carbon footprint savings. Ballast protection pads, something that we also are aware of, and that many operators are moving in that direction. And for our system here, it'll be actually quite easy to apply after the wrapping. There's two options. One is we can project a polyurethane material onto the bottom side of the tie to build up the pad. And the second one is a standard polyurethane pad can be glued to the FSC wrapping, which will provide a very much superior adhesion than you can achieve by just having to try and glue it straight to a complete concrete bottom section. There will be a very high adhesion where the FSC wrapping is. And we also, because FSC is also in the machinery business, we can provide the machine for applying the polyurethane. So what we have here is it's new, it's very empowering to designers, and it's really a maximization of the material properties of the key materials, concrete, fibers, and resin. And all three of these have been around for decades and decades with long histories of performance, high performance in the field. There's no magic pixie dust we throw in the mixer for this stuff. It's just three very common, well understood materials, but used in a very new and innovative way to maximize their physical characteristics. The concrete part we know has poor tensile strength, but it's very good. It has pretty good fire resistance. It's got high compressive strength. The fiber roving is higher tensile strength than steel, higher fire resistance, but it's got a lower MOE than steel, and which combined with the pretensioning of the fibers delivers that flexural strength. And the MOE of the fibers is much closer to that of concrete than steel is. So that's part of the thing here, that by putting this fiber on there in the way that we're doing it, it works quite well with the concrete. The resin has no structural impact or role in the process here. It's used more as an application aid. It helps spread some loads around and eliminate a concentration of loads on particular single fiber filaments. And in the case of pipes and poles, at the end of the process, you have an impermeable barrier on the outside of the pipe or pole. And going back to one of the original points about what the ideal reinforcement will look like, we talked about getting rid of shear transfer. This system does not use that. It's dependent on filament to filament friction. And you can take the product like a pipe or something and go put it in a kiln, burn off all the resin, and then put it back in the test rack, and it'll perform virtually identical to the one where the resin was on there. So it isn't. It's an aid in production, but that's really kind of the end of it. Other than the really valuable element of a waterproof impermeable layer on the outside. Okay. Now there are lots of fibers on the market, from glass all the way to carbon, but for the railway ties and for most civil engineering construction applications, it's mostly going to be glass or basalt. There's some applications fiber or carbon might be useful, but carbon is so expensive that It's not for mass-produced products like pipes or ties. But probably the best one for rail ties is the basalt fiber. It's inherently UV resistant, corrosion resistance. It won't burn in a fire on the track, and it's very cost effective for the value it delivers for the long life of the precast element. And we're preparing now to get into the specification approval program at MXV, which is the renamed Transportation Technology Center in Pueblo, Colorado. It's a wholly owned subsidiary of the American Association of Railroads. And if you want to get a new product into the North American railway market, like a new tie like this, or pretty much most anything, you start with MXV and go through their testing protocols before the railways are going to take a look at you and allow you into their system. So again, as we mentioned it, the origins of this came in the concrete pipe industry, trying to figure out how to make concrete pipe more competitive in the market and to get rid of some of the negative things that steel has. Claudio was the CTO, Chief Technical Officer of the largest concrete pipe production machinery producer in the world, a company called Hawkeye Petershop, now called Affinitas. But anyway, he was tasked with trying to start this process and figure out what was going on and if there's something else we could do. And the use of steel reinforcement, which has been around for 100 years in the concrete pipe business, but the issues with it caused a lot of market erosion in smaller diameters. And again, the goal is to find a new way to reinforce pipe. Other applications for the railway industry include pipes, poles, and then we'll mention briefly later on hyperloop vacuum tubes. So issues with the original very first concrete pipes in the early 1900s, late 1800s were all unreinforced, but when they take any kind of a sharp load, they can fail in this, what they call this 4-hinge failure that you see on the left. The reinforcing it with steel, if you don't have everything right, you're going to see this kind of a situation and have less than what you'd hope for a life cycle. And the plastic pipes that have been moving into the marketplace have their own set of issues, including one of an inherent lack of strength by themselves as a structural element. They depend highly upon a very even and consistent layer of compaction around the outside of the product. So again, we go back some of the benefits here: the cost, CO2 savings, the corrosion. We can now make regular simple concrete pipes that have pressure capabilities up to 3.5 bars. Because of this outer impermeable coating, you can lay them on aggressive soils like sulfate soils that attack the actual concrete itself. And for jacking pipes, there's an additional benefit of not only of a sleek and slippery outside, but but it provides, depending on how you wind it, some additional axial capacity, and that's where the big loading is in a jacking pipe is when you're pushing on the ends. You get some added compression capacity by wrapping the pipe. Poles is another application, and a pole, you can think of it as it's a pipe only stood on end. We can make a concrete core with a conical ID. There's will be a long life cycle. The pole mass reduction, we estimate between 25 and 50%, which will drive the cost being lower than current concrete poles. Also drive down the carbon footprint savings of poles. And because there's no reinforced steel reinforcement in them, they, of course, have a lot lower electrical conductivity than current poles. Yeah, Hyperloop vacuum tubes is there's a lot of discussion worldwide about transportation systems being built around this concept of a Hyperloop vacuum tube, and we're in a consortium that's bidding on some work in Italy for a 10-kilometer test, full scale, full height, full diameter Hyperloop tube. And we'll be the engineering consultancy regarding doing the tube out of concrete, 2 half-concrete tubes, rather than making the whole thing a steel tube. So what we see here is there's some drawings we made for this proposal to do this in concrete rather than steel. So we won't dwell on that a lot. Some of the other applications that we have out there are of course, ultra thin concrete pipes, concrete blocks for high demanding structures, retaining walls, and especially in places with high wind loads and earthquake seismic potential, reinforcing the blocks and then gluing the blocks together is really provides a superior wall performance, which we've done tests on, but that's not the subject of today's discussion. The same thing with large format pavers. We've started work doing some testing with manhole covers made out of concrete. We've had a lot of discussion with companies about pipes for hydrogen storage and pipelines. And by being able to wind individual elements like big blocks and then gluing them together, you can create some really large objects, including things like offshore, onshore wind towers. You can make segmental bridges, and we have a whole system for beams and columns in the works as well. So there's a lot of other applications, but today's focus is really about the possibilities for the rail industry, and hope that you got something out of it. And I guess with that, we'd open it up to questions. I don't see anything in the chat box up there, or no, there's something in there now.
Yeah, brilliant. Thanks for that, Mark. Yeah, I think we've got one question in the chat, which we'll start off with. If anybody else has got anything else, yeah, feel free to raise your hands, or if you prefer to post in the chat, and we'll obviously run through them with Mark and Claudio. So the first question we've got is from Stuart Corrie, which is, how would a sleeper built this way perform under derailment conditions?
Audrey, do you have a thought on that, or? Are you muted? Okay.
Okay. Under derailment condition, what the risk you mean of having the road, the wheels cutting the fiber?
That was my first thought. Yeah. Or is it too recessed to matter?
Yeah, the fiber is actually pretty tough to be cut because it's resin impregnated. So it's not that such a big of a risk in any case, because in any case you have below you still have the concrete. So basically the fiber itself is relatively tough. It's not something that you shear very easy.
Okay, thank you.
Yeah, thanks for that, Claudio. Thanks, Stuart. I think the next person with a hand up is Decoin.
Yes, good evening, everybody, and good morning, Mark. I believe it's morning there where you are. So
Well-
thank you very much for your presentation. Good, very good presentation. So I'm gonna load you with 2 questions now. You may not be able to necessarily answer them straight away, but maybe if you take away it as a consideration. So the first question is around: have you tested the ties in a live environment railroad, or railway as we call it here, whereby you've got train detection systems fitted with it? So for instance, audio or radio frequency track circuits. So as we've learned in the rail industry in the UK, is that audio frequency track circuits, which are used quite widely across the world, they're predominantly now derived from a Canadian form of train detection, whereby the audio frequency is sometimes short-circuited by contamination, dirt, water, and other means on top of the sleeper or on top of the tie surface. So have your reinforced resin fibers been tested electrically for radio and audio frequency for their resistive, conductive, and capacitive properties? And have they been tested in an area which is containing audio track circuits and has, say, for instance, radio frequency balises fitted to sleepers? So, for instance, if you've got a Euro balise fitted to that sleeper, how is that affected when the power from the train's balise receiver powers the balise as it's passing over it and its effect on it? So does the reinforced fibers act as an antenna or aerial, or even change the resistive, conductive, or inductive capacity characteristics of that? That's the first thing. And secondly, what are the recycling how do we recycle these sleepers at the end of their life? Is the reinforced fibers able to be recycled in a sort of carbon neutral, carbon positive sort of way? So that's my 2 questions for you at the moment.
Okay, so from an electrical standpoint, obviously is an insulator because it's a resin and the fiber, both they are not conductive. But we haven't done any specific test. The only test that we have done, which is not exactly the same, but has been tested to testing that kind of wrapping to microwave, basically transparency, because we are using that to make the system. We are using that system to make actually reactors that are heating, basically to make a vessel that is under pressure and is heated by microwave, the internal side. But we didn't do any test yet on conductivity. Sorry, go ahead.
Yeah, I was going to suggest that is an absolute must for testing for the UK rail industry. I would suggest. I'm not an expert in that. I'm an expert in other fields, but where we have particularly older type concrete sleepers in the rail industry in the UK, they create what is called a like a battery effect on the track circuit, which is called a residual voltage, whereby they retain memory electrically. So we know that that's now a phenomena that we're receiving now. We're seeing even with sleepers that are up to 60 years old. So testing for audio frequency track circuits and testing for residual voltages on DC track circuits, which are forms of train detection systems, and certainly testing under where we're going to have Euro balises, which are going to are becoming ever so commonplace in the UK rail industry, with the introduction of ETCS, with the introduction of selected door opening, and other forms of communication to the train, automated communications with the train, is an absolute must for us in the industry. But sorry, I'll let you answer the second question. Sorry.
Yeah. I don't think, we haven't done any test, and obviously we will do it, but I don't think it will be that difficult to achieve to pass any kind of test, because since we have a little bit of resin inside, you always can play a little bit with some compounds and placing, let's say, a little bit of more or less conductive compounds into the resin. Basically, you can tune to the characteristic that you want, even from that standpoint. About the recycling the tie is actually a lot easier than recycle steel reinforced tie, because first of all, you are breaking the concrete that has a ceramic behavior, and the fiber itself stay separated that immediately. It's not that you have such a big difficulties to separate the two things. And then the fiber, the composite that you have, you can basically cut it and you use it as a dispersed fiber into the concrete. Is a lot better than obviously a dispersed fiber that you are normally using in the concrete, because this is already impregnated. So you are having something that is more similar to steel fiber than rather a regular PPE or any other glass fiber. But it can be easily recover everything. It's not difficult to do.
Say, Deck, I'd like to ask you a question. Do you have is there a document that goes into the discussion about what your first question was regarding these electrical issues? Is there a network rail document or something somewhere that we can take a look at?
Well, that's not my area of expertise, unfortunately,
Okay.
Mark, because my area of expertise is in in effect the stewardship of the rail industry rather than the development of the rail industry.
Yeah.
So you'd have to speak to our technical authority of that, and it would have to go through what is known as a DFR, which is designed for reliability, which is in effect your destructive testing and its whole life cycle and how it meets our standards. So you'd need to speak to our technical authority for that. But as somebody who's dealt with audio frequency track circuits, rail detection systems in the UK for a long time, it doesn't need to be copper to conduct between rail to rail. And that's why things like the pads and insulations we have in track circuits, and where we've got unusual characteristics with older types of concrete sleeper ties, as you call them, form us quite a lot of problems. And those residual voltage readings that we get from a particular track circuit are actually safety critical in some respects. They can in effect false feed a train detection system in that respect. So it is really important. Now, you think that just because you think that it's some form of fiber that is insulated, but when it comes to audio and radio frequencies, if that fiber is damp, it will conduct audio and radio frequency sort of voltages. It would just conduct them. We have situations in the United Kingdom where, if, for instance, we use the glass reinforced fencing that is used to protect staff from the track through a tune zone of an EBI 200 track circuit or an ETI 400 track circuit, it will actually short circuit those track circuits if it's raining, as an example. So, glass reinforced fiber fencing is conducting audio and radio frequencies through them. But more than anything else is the fact that we're moving over to ETCS and the ERTMS systems, which are more about radio-based police systems in the track. And those radio-based polices are going to be mounted in the track itself, actually in between the rails, what we call the forefoot. And they're non-powered radio-related devices that the train, as it comes to them, has a receiver and an antenna on it that is so powerful, it powers them on their approach. So it's providing a huge amount of energy, radio energy, to that radio police for it to become self-powered as it becomes close to it. So I'm wondering if you've ever tested these ties in a situation where we've got Euro polices, which are used throughout Europe and now are going to start being used globally. Because if they don't work with Euro polices, then your product won't work with the future rail industry. So it's important that that's tested beforehand. Regardless of the ETI 400 and the EBI 200 type train detection systems that are out there, that could be short circuited by the fact that water is in the channel, and it allows a conductor for the radio or audio frequencies across the rails to basically cause a track circuit failure. Regardless of that, because we're moving towards Euro polices, they really need to be tested with Euro polices to ensure that they work and they do not disturb, interfere, or change the characteristics of Euro polices. Because other than that, if they do, then the product would need to be modified for use in the UK. So I'm wondering whether your testing regime has been robust enough to accommodate that. If it hasn't,
Oh.
take it away and have
Yeah,
a think about
no.
it.
No, you know, we haven't done that level of testing, and that's why I was inquiring about where we can go look and see what kind of tests that would need to be performed and get some research on it. But thank you for the great question. That's a good point. It's something to really dig in and know about.
So if you want to move any further from that, perhaps contact Martin Jones, who's Network Rail's chief engineer.
Okay. Thank you.
You contact him on LinkedIn as an example. He's there on there. His name's Martin Jones. He's our chief engineer.
Yeah, thanks for those questions, Deck.
Martin Jones, sorry, the name.
Martin Jones. Yeah, I've got it.
Okay.
I
There's
think.
That's the one.
Sorry, Mark.
Martin with an I, an India, not a Y, a Yankee.
Yeah. I see a question here about the FSC sleepers being aimed at marketed just in the USA at the moment, or are there ambitions to seek approval for use overseas, such as the UK? Absolutely, there is. We're working with a couple of railroad groups, and like I mentioned on the continental part of Europe, those ties that you saw being wound. The video was of ties provided to us by local producers. So we're moving. We're going to be moving in that direction as well. The thing about the U.S. is we have one agency for all of U.S. and Canada to move through the testing cycle on, and B, 97% of all the ties in North America are still wood, but the railways want to move away from that and go to something else, concrete. They've tried some composite ties, but they know that wood, because of how often they've got to replace them, that's not a long-term thing going forward. But they're looking for something else, whereas Europe is mostly concrete. It's the other way around. So the U.S. is just this giant ripe market, and it's one agency to deal with for the entire continent. Basically the entire continent. So that's why I mentioned the MXV thing, but the intention is to also pursue it in Europe as well.
Brilliant. Thanks for that, Mark, and thanks, Liz, for the question. I think, David, you're the next with your hand up.
Yes, cheers. Thanks for that, Pete. I've got 3 questions. I'm hoping to go through them fast. First one is resonance and dampening. So concrete we have a problem on quite a lot of our very old bridges with resonance from concrete through into them. We still have to use wooden ties. How have you found these compare to concrete sleepers and wooden sleepers for responding to high frequencies due to dynamic loading?
So basically, the graph about the strength that you have seen has been obtained with just 4 MPa post compression, which is almost half of the pre-stressing that you normally have on a rail seat, and is about 1/4 of of pre-stressing level that you have on the central section of a regular tie. That help a lot, obviously, and another things that help is that you can actually tune the sleeper as you want, because you can add some radial wrapping, and basically playing with the free length that you have between the, let's say, the adhesion. You control the adhesion between the tie and the wrapping. So actually you can tune it to the frequency that you want to have the self frequency that you would like to achieve.
Okay. That might actually be one of your selling points, Mark. In the UK, if you can replace long timbers on rail bridges. The second one is wet strength. Having just come off a series of GRP failures in drainage, and reviewing the literature, the strength of GRP and FRP generally has been found to reduce to about 30% over a couple of years when left in a wet or damp environment. How have you found yours to respond to wet and damp environments?
Basically, we have a very different system of transferring the load. Instead of we are not relying on the basically on the glue, on the matrix, on the resin. Since we are wrapping, when we are wrapping and we are pull it roughly at let's say 10% below the creep limit of the fiber, and this is creating a gigantic friction between the various roving. That is the reason, even if we are burning out completely the resin, we are not losing any strength. That decreasing of performance happening because you have problems, you have changing in the resin. Typically, if you are using polyester, obviously is like a lot taking water. If you are using epoxy, a lot less. But in our case, is insignificant in any case because the resin is there just to provide toughness. Because obviously, if you have just the bare fiber, if somebody get there with a knife, you can cut them through. So we need the resin just to provide surface toughness. We don't need to. We need it because obviously when you have the ballast side, you need to have that toughness. Otherwise, the ballast is cutting through the fiber, but it's not transferring any load, the resin. So we haven't done anything on the tie, but we have done on pipes. So we left pipes out for years and then tested, but there is no difference. It's not like on a GRP. And another big difference is that because we don't have a delamination risk, that's another big situation. Yeah. Because everything is in tension always. You normally have a delamination when you get compression. Yeah. In our case, the fiber is always in tension. It's not getting compression.
I wasn't
ever.
worried about delamination. That's actually on my positives column. The last one is high impact knife cutting loads. So obviously you're directly contact with ballast and tamping. And if there's one thing that we know happens with concrete sleepers is that lots and lots of tamping, add a lot of ballast, generally add a lot of water to help with the scour as well. You end up with quite a lot of erosion of that cover level into sleepers. One of the problems that concrete sleepers currently has with removal of its cover depth, which you've already referred to. Obviously, you've put the critical element on the outsides directly interfacing with the ballast. How have you found it deal with cutting loads and sharp point loads?
We had the same question in US because we did the presentation. So a few months later, we did a very, not very, let's say, well, is a wear test that is used for those kind of things, but we did in our lab, so it's not certified. But basically, if compared to a concrete ties, we have a mass loss that is about 1.9, so almost 10 times less. It's pretty tough, that material. It's basically not that different from a fiberglass tie. It's the mass loss is not that significant. And it's not that you have 1 millimeter of fiber. Typically, on a tie that is 230 by 180, you have probably a layer that is around 5 or 6 millimeter on each side all around. So it's not that a small scratch let everything fail. Just to give you some background, one of the application is on the pipes is for jacking pipe under rails because you can avoid to have steel reinforcement in that way, which is not at least Italy and Germany, they don't like very much have a steel reinforced pipe because conductivity and so on. So we passed through the test about jacking pipe which is a much harsher than just having the tie sitting on a ballast, and actually it went much better than what you have with a concrete pipe, because it's relatively strong. The surface is not that.
Cheers, thank you. And just a helpful tip: if you bring up the removal of a hidden critical element, steel being hidden critical element within the concrete, bring up that bit. That's a buzzword over here, especially in the civils world.
Brilliant. Yeah, thanks for that, David. I think Stuart had another question, but it looks like he might have just had to take another call. So I know Dex raised a point as well in the chat about the use of the railroad test facility at Pueblo in Colorado, which is one I've come across before in other PWI presentations.
Yeah, that is
yeah,
the facility. I texted in the text box there an answer to his question there. It is the facility. It used to be known as the TTCI, but a little over a year ago, and it's a long story, but they ended up building a whole new test facility and rebranded themselves as MXV, which is mass times velocity, so equals momentum. So they made a little thing there about branding as mass times velocities, meaning that they're an organization headed towards momentum. But they were running that facility, the original facility, under contract to the U.S. Department of Transportation since the 80s, and they put the management deal out for bid, and TTCI didn't get it, and so the American Association of Railroad Board decided that, hey, we're gonna go our own way here. There's enough problems with this facility, that things that we don't like. We're just going to build our own new facility, including lab and everything. And it's a lot closer to Pueblo. It's not way the heck out in the prairie there, way out of town. So, but that's just in the getting close to being reopened now.
Well, we have 3.5 test sites in the United Kingdom. And those 3.5 test sites, and why I use the word half is one's under construction. So we have 4 light rail systems and 1500 volt DC overhead line systems. We have the Tainawea Metro test system up in the northeast. Then we have what is known as the Old Dalby Test Centre, which was a piece of old railway that was a main line that was converted to high-speed route for testing of high-speed trains in the 1970s. And they still test trains on there at the moment. But Network Rail has a test site at a place called High Marnham, which was a former colliery with a vast and extensive rail system over in the east of the country. And at the moment, the reason this is where the half is that the industry, the rail industry in the United Kingdom, is building a new test facility for all aspects of rail engineering, whether that be rolling stock, traction, or infrastructure in South Wales. And that particular test site in South Wales is deemed to be a carbon neutral one as well. So it has been flagshipped as our future. So just a thought, if you come across with Martin Jones or whatever else, if there's an offer of, testing your ties, maybe the introduction of those ties into the newly constructed, or the construction is about to begin of the site in South Wales for the test centre might be an option, rather than the Colorado one, which is where we tested Britain's tubular stretcher bars, which were tested to destruction there, and it was a good site at the time that it was done. So sorry for chipping in without my hand up.
no problem. Thanks, Dick. So yeah, there's just I suppose we're past 5:30 now, so it's probably just good to wrap up. I think in the chat, Mark's provided the FSC info email address for anyone who needs any additional information. So thanks very much for that, Mark. I know Marco has also added a note there that the presentation will be a lunch and learn event in September later this year. I'm not sure if anyone on the call has dialed into a lunch and learn event before, but I'd highly recommend them. So it'll be really good, I think, to pick this up with a larger audience later in the year. So yeah, I suppose it just it's up to me now to say thank you very much to all three of you for coming along today to present to the section. It's been a really interesting presentation, seeing the wide variety of potential applications for the technology in the rail industry. One particular one which I think could be worth looking into is the application of this technology in slab track. I don't know whether it's called slab track in Europe and the USA, but non-ballister track systems. When you're mentioning the damping properties, it really did make me kind of quite intrigued as to whether there is potential application for this system in things like the London Underground and other metro systems where damping is a pretty serious consideration. And I think as well, just the general content in the presentation about the material properties was really interesting to see. So yeah, thank you very much, Mark, Claudio, and Ronaldo. There's a lot of thanks as well in the meeting chat. So we really do appreciate you coming along to present to us today.
Well, we thank you for having us.
Thank you.
Brilliant. Just before we finish up, just one section announcement.